Hello everyone, welcome to CS412-Software Security. This is the speedrun of OX08 testing, and today we're going to focus on sanitization. Let's start with the learning goals for today. Testing requires an oracle to mark a bug, and therefore we require a way to figure out that a bug has actually been triggered, and we require a signal. Understanding what this signal is and how this signal works is a key component of today's class. We also want to understand different sanitization policies and how sanitizers can enforce strong policies. Be aware of the trade-offs between precision and performance overhead, and discuss the limitations of individual sanitizers. As we're focusing on sanitizers, we have to make sure to understand the necessary goals and how sanitizers actually enable us to find new kind of issues that are different from other parts that we would be able to find without sanitizers. The key goal of sanitizers is to crash early and quickly. So the idea here is that we would be able to signal a potential issue as quickly as possible. A sanitizer will instrument the target program to check for violations to make sure it crashes immediately when the bug is being triggered. Now, compare this to, for example, a fuzzer trying to find bugs in a program that has not been instrumented with a sanitizer. Right? So the fuzzer triggers faults and records crashes, but not every fault actually crashes. If you're considering memory safety as a policy for a second, this would mean that, for example, a 1 byte overwrite or a 1 byte overread behind or past the end of a buffer may not immediately crash the target program, but may just let it continue with slightly wrong data. Now, with a sanitizer, we would crash, or the sanitizers would crash the target program right when the bug happens, right when this illegal read is actually about to execute, but right before it executes. Now, without a sanitizer, the program state may be compromised arbitrarily and may continue potentially until it completes and just gracefully exits, or at a weird bug at a later point in time. Now, what we want is at the very first violation, we want the program to crash and simply stop execution. So sanitizers enforce the security policy to crash the program upon a violation to find and expose bugs. So sanitizers inherently make faults detectable, and at least much more likely detectable. So sanitizers can be probabilistic, and that's one of the reasons why they are not a mitigation. But we'll discuss this in a bit more detail in a little bit. So sanitizers enforce a policy to detect bugs early and to increase testing effectiveness. There's this inherent trade-off between performance, overhead, and additional checks executed that we'll also discuss later on, and you can keep in the back of your head. So a program is analyzed during compilation, for example, to learn properties such as type graphs or to enable different kind of optimizations. And the program is then instrumented during the compilation. So for a given policy, certain operations will be instrumented to record metadata for the later checks and to execute the policy checks at different kind of places. At runtime, this instrumentation then constantly verifies that the policy holds. Now, as an interesting question here is, what policies are interesting, right? What would we want to have for a checking policy? What metadata is needed, and where do you check? Now, the very first and simplest policy is address sanitization, that enforces some kind of memory safety policy. An address sanitizer tries to check for memory safety violations through pointers, where a pointer may point to a buffer that is not allocated memory, or may point outside of a buffer of allocated memory. So address sanitizer instruments each memory dereference and checks for a poison value. So for example, there's this buffer that is allocated, as you see in the figure on the right-hand side. An address sanitizer will place 2 red zones. These are 2 no-go zones right next to the buffer before and after it. When a pointer is being dereferenced, AddressSanitizer checks if the pointer points into the red zone. If it points into the red zone, then the program is being terminated with a message that says this was an illegal access. The advantage is that these checks are rather fast, and the policy is highly compatible with, for example, uninstrumented code or inline assembly, mixed targets, and whatnot. Disadvantages are that there's still fairly large memory overhead of up to 3x, and especially on 64-bit systems where pointer values are a bit wider and the address space is much bigger. It's still slow, so it's still about a 2x overhead. And last but not least, AddressSanitizer is not a mitigation. So even if you were willing to pay the 2x overhead, you could not use AddressSanitizer as a memory mitigation, because an attacker that knows that a program is protected through AddressSanitizer could simply adjust their exploit to bypass the AddressSanitizer policy. So for example, a pointer that goes beyond the end of the buffer could be adjusted to then point to another buffer, right? To point to the next buffer where it is again in the red zone. So after the two red zones that you see here on the figure would be the next buffers, right? And the pointer could be adjusted accordingly. But AddressSanitizer is an amazing tool at exposing bugs for developers when you run tests or when you run a FuZZan campaign. Some notes on the Hall of Fame from the official page, right? ASan found over 3,000 bugs in Chrome in the first 3 years, over 3,000 bugs in Google server software, and over 1,000 bugs in open source software. These numbers by now are likely an order of magnitude larger. So there's uncountable numbers of bugs found in all kinds of software through AddressSanitizer. And it's by far the most successful sanitizer that I've ever seen. So AddressSanitizer finds memory address bugs, so different kind of memory safety violations, with a focus on buffer overflows, on the heap, on the stack, on globals, like any out-of-bound access, MemorySanitizer will highly likely detect. There's some support for use after free if the use happens soon enough. So there's going to be some recorded area where previously some buffer was allocated that is then marked for a given time. So the reallocation will be delayed, and hopefully the use after free happens in a time frame where AddressSanitizer can actually detect it. It also detects some spatial and some temporal memory safety violations, and most of them actually. The implementation is as follows. There's a compiler module which is now available in Clang and GCC, and at compile time it instruments all the loads and stores that are then executed with additional checks at runtime. At compile time it also pads stack and global variables with these red zones to make sure that the violations can be detected. There's a runtime module that supports AddressSanitizer to intercept malloc and for some additional bookkeeping. Now in this example here, we've got a simple example that, based on the argument given, has a buffer overflow on the stack, on globals, on the heap, or a simple use after free on the heap itself. Now, without compiling with ASan, all of these, or most of those, would actually continue, and they would highly likely not crash. With AddressSanitizer, all of these 4 bugs will actually trigger a violation, and then we can signal that something is wrong. Now, if you think about these policies, right, how would you implement AddressSanitizer? What kind of metadata do you need? Do you allocate this on a per object basis? Do you allocate this on a per pointer basis? Do you allocate this on a global address space basis? What operations do you instrument? What kind of optimizations can you think of, and so on? And then most importantly, how would you detect out-of-bound and use after free accesses? Think about this for a while, and let's get on a tangent on data structures for metadata. How can we efficiently store metadata? And metadata is like additional data we require about the program. And there's different options, right? So for example, for each buffer, we would like to have some additional data about the red zones next to it. Maybe about each pointer, right? We already had this for softbound. In the simplest form, we can have metadata for our address space by storing it in a flat compressed map. And this is, for example, exactly what ASan does. So this trades space for speed. So ASan takes the large virtual address space, reserves a chunk of the address space, so for example 16 terabyte in a 64-bit address space, as the figure on the lower right shows, and thereby enables a very efficient lookup. So each 8 bytes in the address space have a corresponding 1 byte metadata value. And we take this base address plus the address shifted by 3 and then thereby get the location for our target address in the metadata array. Another option would be a 2-level lookup data structure similar to a page table implemented in software. So you would take the address where the pointer is, or where the pointer points to, for example, break it into 2 parts, look up the first pointer, and then follow that reference to the second layer page table, and then read the metadata. This trades some speed for space because we have 2 lookups at the same time. The last option would be a red-black tree, which trades a lot of speed for a lot of space. Right? So the flat compressed map requires a massive amount of virtual address space, but is fairly performant to implement. The red-black tree is terribly slow, but requires very little space. So you've got the 2 points on the design scale here, allowing you to choose which one is the most efficient. And AddressSanitizer and all the other sanitizers require really fast lookup, and they don't mind the waste of virtual address space. What's 16 terabytes of virtual address space between friends? As certainly not all of it will be allocated in practice. And this is just virtual address space that will be given, will be allocated on demand whenever it is actually needed. Now, the issue here is that you still need to allocate the page table data structures in the kernel, and this will cause some overhead, as we'll see later. So what kind of metadata do we actually store? The idea that AddressSanitizer has is that it stores the accessible state of each word in shadow memory. Now, we have 1 byte of metadata for 8 bytes of memory. We could just store 1 bit of information about the accessibility of each byte. But this doesn't allow an efficient check, because then we would have to do bit fiddling and whatnot. A more efficient way to encode this is to simply store how many bytes are actually accessible. And the value in the metadata stores how many bytes are accessible from the beginning of this 8-byte region. Just 1 byte, 2 bytes, 3 bytes, 4 bytes, 5 bytes, 6 bytes, 7 bytes. And if all the 8 bytes are accessible, we store it as a 0. Right? Because this allows us a very efficient check if we go for the full 8 bytes. So the encoding assumes that only the first k bytes of a word are accessible, and the shadow entry stores the number k for each word. Larger words translate to smaller metadata usage, right? So we could reduce the amount of space we need for the metadata table. So instead of 16 terabytes, if we go for 16 byte words, we would only have 8 terabytes. If we go for 32 byte words and so on, this would just reduce it one after the other. So larger words reuse as each word maps to only one object, right? So this is the downside of it. If you use larger words, we have a smaller address space, but we also have like less reuse, because there can only be one object in one of these chunks, right? So this is like a trade-off you have to do. And now if we use this encoding, we can have a very efficient metadata access. So ASan maps real addresses to shadow address. And by doing a shift by 3, so we get rid of the 8 bytes that we have here, and we add to the shadow base, right? And then we have the address in the shadow metadata table. Address is the original address, and shadow base is the base address of the shadow metadata table. If you want to check if a word is okay, right? If you want to access 8 bytes in memory, then a check looks as follows. Before, like a simple memory deref, like asterisk address, becomes a call to get data that is then being inlined. And this would be like adding address shifted by 3 to the right to shadow base, and then checking if this is true, like if it is non-zero, and this is where the 0 value comes in, then we report an error. Otherwise, we dereference address and return, right? And this is of course inline for optimization. But every single memory deref now becomes this access, where we calculate the target, shift by 3, and then do a check of the metadata value. If we do a partial access, right? If we do a partial word, then we have to do the check if all the bytes are actually accessible. And here we have encoded a check for the first 4 bytes in the word, if those are accessible, right? And as you see, this is where why we need this optimization for all the 8 bytes, because most of the accesses will be all the 8 bytes. If we do an arbitrary access, like of n bytes, we actually do the check address and 7 plus number of bytes minus 1, and bytes can be 1 to 7. Otherwise, we report an error. Now, let's figure out how we do the instrumentation for the allocation. Like when we allocate objects, we need to record the areas of the red zones in our metadata, right? For the stack, we just insert red zones around the objects on the stack and poison them whenever we enter the stack frame. When we exit the function, the epilogue removes these red zones. So the prologue will initialize it, and the epilogue will remove the actual check. So if you have this simple foo function here with 8 bytes of an 8-byte array that is then being used later on, ASan would change this as follows, right? It would insert a 32-byte red zone before, the 8-byte buffer, add a 24-byte red zone as padding, and then at least a 32-byte red zone later on to make sure the alignment actually works out. And then to poison the value, to record that, hey, these bytes here cannot be accessed, like the 32 bytes before the buffer and the 56 bytes behind the buffer, it would record that, hey, the first 32 bytes are not okay. Then the next 32 bytes, out of which 8 bytes are okay, we would poison the red zone 2, which is 24 bytes long, and then poison red zone 3, which records that all of this is not okay. So OXFF for a byte says that all the 8 bytes are not accessible. Right, so far so good. And then when we exit in the epilogue, we remove the shadow values again, thereby clearing the metadata and making sure that future accesses do not trigger. And the clearing afterwards is especially how we make sure that this actually works for continuous for later function calls, thereby guaranteeing that they can actually be safe. Right? So AddressSanitizer, when an object is being allocated, it creates the padding around it and then records that this padding should trigger a fault in the metadata. When the data is being freed, it actually clears these red zones afterwards. Let's look at globals, right? If there's a global value here, a global value, an original value, we will add a red zone of 60 bytes around it. Of 58 bytes around it, sorry about that. Yeah, so we'll create a red zone of 58 bytes, of 60 bytes around it to have a total of 64 bytes that is 32 byte aligned. Right, so the original integer will have 4 bytes, the red zone 60 bytes, which gives us, same as for the stack before, a 32-bit unique red zone. So 32 plus the 28 bytes gives a total red zone of 60 bytes. In addition to that, we have the runtime library of ASan, which initializes this shadow map at startup, right? Luckily, whenever you allocate memory, it is all zeros, so this is fine. So it just mallocs or nmaps this massive area. And then malloc and free, they're being intercepted to update the metadata and to pad objects with red zones. And the runtime library also intercepts special functions such as memset and string copy to make sure that they can actually work. So AddressSanitizer detects memory errors by placing red zones around objects and then checking those objects on specific trigger events. The tool detects quite a bit of issues. Out of bounds accesses to the heap, to the stack, and to the globals, use after free, use after return, use after scope, double free, invalid freeze, and so on. For any use after something, it makes sure that the data remains marked for as long as possible. So it will delay upon free. It will simply mark the whole object as being free in the metadata. So the whole memory area, the red zone and the object itself, will become a red zone, like one gigantic red zone. And then it will delay reallocation for as long as possible. So until the program runs out of memory. And this allows us to detect some use after free errors, but not all of them, because at one point in time it will have to be reclaimed. A typical slowdown introduced by AddressSanitizer is about 2x, and you can run this readily on any of your code by compiling this clang fsanitize equals address, my target. MemorySanitizer is another sanitizer that detects uninitialized reads. So memory allocations are being tagged and initialized with all ones, for example. And whenever an area is being written, then on memory write, the bits are being cleared. And on memory read, it makes sure that the bits are actually cleared. So MemorySanitizer allows you to detect any kind of uninitialized reads. Typical slowdown of MemorySanitizer is 2.5 to 4x, with about the same amount of memory overhead as AddressSanitizer. Do not confuse MemorySanitizer and AddressSanitizer. AddressSanitizer gives you an approximation of memory safety. MemorySanitizer gives you this protection against uninitialized reads. Next on the list is UndefinedBehavior Sanitizer, which detects, as you would have guessed, any kind of undefined behavior. It instruments code to trap on all the different kind of undefined behavior in C and C++ programs, such as unaligned, misaligned, unsigned pointers in different weird ways, signed integer overflow, which is undefined behavior, conversion between floating point types leading to overflow, and illegal use of null pointers and then illegal pointer arithmetic. The slowdown really depends on the amount and the frequency of checks, and it's the only sanitizer that you can actually use in production, because usually the overhead is rather low. For production use, there's a specific minimal runtime library that has as little attack surface as possible, and would simply detect that, hey, there's this undefined behavior that is being triggered that could be exploitable, and therefore the target program is being terminated. ThreadSanitizer is another one that finds data races between threads by keeping track of which thread is writing what data and then looking at the sequence of reads and writes. Multiple threads of execution share an address space. The same variable accesses to the same target requires a protocol, or at least locking, These accesses must be ordered if at least one of the threads writes, and ThreadSanitizers detects these data races between threads by like figuring out which thread wrote which heap or stack variable last, and keeps track of the synchronization primitives. Slowdown is fairly drastic, like a 4 to 10x slowdown with 5 to 8x memory overhead. So this is fairly hefty. So if you look at the Sanitizer family, like there's a bunch of sanitizers out there. AddressSanitizer, LeakSanitizer, ThreadSanitizer, MemorySanitizer, UndefinedBehavior Sanitizer, hex type to check for type violations, and a bunch of others, right? Check your code with fsanitize equals address. That's the minimum you can do whenever you test, but have a look at all the other sanitizers as well. They've been very well established. They are very well used across testing, and they found tens of thousands of bugs across all of them, if not hundreds of thousands. So it's a massive improvement in bug finding capabilities. Now let's figure out how to speed up sanitization. We've now talked about sanitization in how it works and what the trade-offs of the different policies are, but we'd also like to figure out if we can make this faster. We measured this on AddressSanitizer and discovered that the sanitizer is not optimized for a fuzzing environment. And in a fuzzing environment, there's a lot of executions. Executions are highly repetitive and usually short. And in fuzzing, ASan is incredibly expensive. We found that it's about a 3.4x on average, but up to 6.6x X overhead. So this is incredibly high. And we learned that sanitization is rather costly due to the memory management, the large VM area that is being allocated, and the sparse page table entry. There's also the initialization of ASan and all the additional logging overhead, right? For example, to keep track of which object or which line of code has allocated this object and whatnot. All the metadata that is usually not needed for during a fuzzing campaign, right? And can easily be removed. So just by looking at address sanitization, the number of page faults rises massively, and the number of memory management is also very, very costly, right? So there's 365% overhead in page faults and over 1,000 overhead in memory management time. What we want to introduce is a lightweight alternative with different kind of metadata structures to reduce the sparse page table entries and to minimize the memory management overhead necessary. Then we do some runtime profiling to select the optimal data structure and remove the logging overhead and initialization overhead. So our design is as follows. We have a fuzzer and a target. And the target we compile 4 times in 4 different ways. Once with ASan shadow memory, just as it used to be, right? So this is the default address sanitization. And then we compile it 3 times more, once with sampling to figure out the cost of the execution, and then with an RB tree and a minimum shadow memory, which we will discuss in a bit. And then the fuzzing module will leverage and execute the sampling target several times to measure the behavior of our target program. And key metrics are how long is the execution, how many reads are there, how many writes are there, what's the diversity of the write, and then we determine the optimal metadata structure and switch between these different targets based on the metrics that we collect. So we add and have 2 complementing lightweight metadata structures that we can switch to on demand. AddressSanitizer comes with very high management cost, but the access of the metadata is very cheap, and it supports very large amounts of memory. For FuZZan, on the other hand, we have the 2 alternatives, the red and black tree, which has low memory management cost, but incredibly high metadata access cost of log n. And if there's only very few metadata accesses, as in there are very short executions with few memory accesses, then this is perfectly fine. For min shadow, we have a medium memory management cost, which is much lower than what AddressSanitizer has, and the same metadata access cost as for MemorySanitizer. And the key idea here is to restrict the address space and forcibly shrink the address space of these applications. So the min shadow mode has a lower memory management cost than ASan while keeping the same metadata cost. So min shadow is designed for target applications with very frequent metadata accesses. Okay, so far so good. So how does the memory mapping look like? We've got the original memory map on the 64-bit platform. ASan will allocate 16 terabytes of memory. And what we do is we map this, what ASan does, it maps this into the 16 terabyte map. This includes the 4 terabyte heap memory for the ASan enabled program, and together with the 4 terabyte heap, ASan allocates and reserves around 20 terabyte of memory total, which is quite a bit of memory that it requires. Right, so this comes at a fairly high cost of managing the page tables in the kernel. So the 16 terabytes of shadow memory plus the 4 terabytes for the heap ends up in this 20 terabytes of memory that is actually being allocated and kept. Now on the other hand, right, so this requires 20 terabytes total. With our min shadow, our alternate mapping, we try to condense this to a much smaller space. So we shrink the application's memory space while still running on a 64-bit target to maintain the corresponding compact shadow memory. For example, if you shrink the target application to 4 gigabyte, right, 1 gigabyte for the stack, 1 gigabyte for the heap, and 2 gigabyte for data, text, and zero initialized data, we only need to maintain around 5 gigabytes of memory. Again, the different areas map into our shadow memory and allow us to keep track of all the different parts in only 512 megabytes of shadow memory, and together with the heap and the stack, together with the heap and the shadow memory, this is 1.5 gigabytes of pre-allocated memory. So we've shrunk the address space from 20 terabytes to 1.5 gigabytes that needs to be allocated. Even though this is only a virtual address space, this is a much smaller address space and allows us to improve performance. We don't have just one memory mode, but we actually have alternate layouts for different heap sizes. So we've got the small heap with 1 gigabyte of storage, the medium-sized heaps with 4 or 8 gigabytes of storage, and the large heap with 16 gigabytes of storage. This results in between 512 megabytes of shadow memory and 2.4 gigabytes of shadow memory, giving us quite a bit of options between the different targets. Now, we need to figure out what is the optimal metadata structure during fuzzing. We could switch by hand and select the target before. For example, depending on the analysis of our target program, we could hard code one metadata structure, or we could switch automatically. We want to avoid this manual extra effort and automatically figure out which one is the most efficient target, including the automated switching mode. So whenever the heap size exceeds the support for our target, we would switch to a larger options and then adapt the metadata structure according to the behavior. So we measure periodically the program's behavior, including the number of metadata accesses on the stack, on a heap, and for globals, and the total size of the heap, and then thereby maintain the detection capabilities that ASan has. We use a fork server to avoid unnecessary reinitialization and move ASan to the initialization point before the fork server, and modify ASan to disable logging. The logging can still be completed as the fuzzer creates a witness. So whenever we detect a crash, we can simply rerun the target with this created input for full logging output. If you look at the performance of the different targets, average time of execution is 274 seconds for native. If we only fuzz with the RB3, right, as a target, this is quite a bit of an additional cost compared to just using ASan. So it's like a 2x increase if we only do the RB3. But we'll see where the RB3 is actually useful in a bit. Now, if we look at our minimized data structures, we get a 43% improvement to a 36% improvement. All quite good. So it actually makes sense to use most of these optimized targets by default and to shrink the address space of the target application. Now, the additional optimizations that we perform, these are just orthogonal. These are engineering optimizations. But using these engineering optimizations, we can go from 1100 seconds to 826 seconds by actually optimizing this. That's fairly good. And this is obviously compared to ASan, 19% with the logging optimizations, 11% with the initialization, and 25% if we do both. The two other options with 1 gig and 1 gigabit heap optimized ends in 574 seconds or 632. So 43 to 48% improvement compared to ASan. And if you do the dynamic switching, that's 48% improvement in the best case. But we don't have to switch or adjust. Now, as it turns out, depending on the different targets, we actually have to use different optimizations, right? So here we evaluate the switching that analyzes which of the different targets is optimal for the different areas, and here we see the different runtime behavior. In these first three benchmarks, we see that sometimes we use the red-black tree, and most of the time we use the 1 gigabyte target. For these other benchmarks here, sometimes as the heap is fairly large that is being used, we even have to fall back to ASan shadow memory as it exceeds 16 gigabytes. Right? So here we see that all the different min shadow modes are actually being activated. Let's look at performance overhead for memory management time, and we see that we were able to drastically reduce the overhead for memory management by 62 times, and similarly reduce the page faults by a drastic amount of time as well. So in total, quite a bit compared to AddressSanitizer. Similarly, if you look at executions per second on ASan, we only have 108 executions per second on average, and we are able to increase this by 61% to 174 executions per second. If you look at unique discovered paths, ASan, our optimization to ASan was able to improve by 13%. So overall, this allows us to speed up ASan quite a bit. And it tells us that even though AddressSanitizer is a great engineering tool or a great testing tool, a little bit of engineering that customizes it towards the use case of fuzzing still gives us a bit of a performance boost, enabling us to improve this overall execution. So sanitization incurs overhead, and FuZZan allows us to tailor sanitization to fuzzing. Right? So this is a customization to this use case. Novel metadata structures condense memory space, and the dynamic switching between metadata structures allows us to select the best option at all times and removes unnecessary operations. FuZZan improves throughput over ASan by 48% with provided seeds, and discovers 13% more unique paths in the same 24 hours. And it gives us like this additional flexibility to try out and figure out which are the best possible options on target. So let's summarize today's class. Sanitizers allow early bug detections and not just exceptions, right? So this allows us to detect a bug right where it happens before it does any harm, terminating the application to give the developer most possible feedback. There's sanitizers for different use cases. AddressSanitizers enforces probabilistic memory safety by recording different kind of metadata for every allocated object and then checking every memory read and write. MemorySanitizer targets uninitialized data. ThreadSanitizers targets data races. The UBSAN finds different kinds of undefined behavior depending on what you select. Hex type targets type confusion. So in the end, you need to tailor sanitization for your target and then use one after the other if there is different sanitizers that apply. They don't compose, but you will rerun FuZZan campaigns anyway over a longer amount of time. So select one sanitizer after the other and iterate through them. And in the end, I leave you as a parting note here that you should sanitize all the things during testing using clang fsanitize equal address my target. And this fits into this nice sanitization optimization goal. This is all for today. Thanks for your attention, and I'll see you around for the next class.